Welcome to today's problem walkthrough. We'll be solving LeetCode problem number 1721, swapping nodes in a linked list. In this problem, we'll explore swapping the kth node from the start with the kth node from the end in a singly linked list. Let's dive in and break it down step by step. In this problem, you are tasked with swapping the values of two specific nodes in a linked list. The nodes to be swapped are determined by the integer k. Specifically, you need to identify the kth node from the beginning of the list and the kth node from the end of the list. Since the linked list is one-indexed, the first node is at position 1, the second node is at position 2, and so on. If the list has exactly two k1 nodes, the kth node from the beginning and the kth node from the end will actually be the same node, so no changes will occur. After performing the required swap, the function should return the head of the modified linked list. The input includes the head of the linked list, which is a list node object, and the integer k. The output is the head of the updated linked list after the swap has been executed. To better understand the problem, let's look at a concrete example. Suppose the linked list is 1, 2, 3, 4, 5, and k is 2. The second node from the beginning has the value 2, and the second node from the end has the value 4. When we swap their values, the linked list becomes 1, 4, 3, 2, 5. Notice that the positions of the nodes themselves don't change, only the values within those nodes are swapped. This highlights the key operation in the problem, identifying the correct nodes and swapping their values. Now, consider another example where the linked list is 7, 9, 6, 6, 7, 8, 3, 0, 9, 5, and k is 5. In this case, the fifth node from the beginning has the value 7, while the fifth node from the end has the value 8. Swapping these two values results in the linked list 7, 9, 6, 6, 8, 7, 3, 0, 9, 5. Again, the nodes themselves remain in place, but their values are exchanged. For a simpler example, consider a linked list with just one node, 1, and k equals 1. Here, the first node from the beginning is the same as the first node from the end, meaning there's no actual swap to perform. The linked list remains unchanged as 1. It's important to note the constraints and edge cases for this problem. The number of nodes in the linked list can be as large as 100,000, so your solution needs to be efficient to handle these larger inputs. When the list has only one node, as we saw earlier, no swap occurs because the kth node from both ends is the same. Similarly, when k equals 1 or k equals the length of the list, you are swapping the first node with the last node. For even length lists, if k corresponds to the middle of the list, the swap logic must handle this symmetry correctly. These considerations, along with the large input sizes, make careful implementation essential to solving this problem effectively. To solve the problem of swapping the kth node from the start and the kth node from the end of a linked list, we begin by considering a brute force approach. The intuition here is straightforward. We first determine the positions of these two nodes within the list and then simply swap their values. To achieve this, we can use a two-pass traversal. In the first pass, we calculate the total length of the linked list, which we denote as n. In the second pass, we locate the kth node from the start and the kth node from the end. The position of the latter can be calculated using the formula nk plus 1. Once both nodes are identified, we swap their values directly. This method is simple to implement and has a time complexity of O(n), as it requires two full traversals of the list, while the space complexity is O(1), since we only use a few additional variables to store pointers and counters. While the brute force approach is conceptually simple, it has trade-offs. The need for multiple traversals makes it less efficient, especially when working with very large linked lists. To address this, an optimized one-pass approach can be used, leveraging two pointers to locate the required nodes in a single traversal. The key insight here is that the kth node from the end is separated from the kth node from the start by two k nodes. By maintaining two pointers, where one lags behind the other by k steps, we can pinpoint both nodes in one pass. This eliminates the need for a second traversal, making the approach more time efficient while still maintaining constant space usage. The optimized one-pass solution involves carefully managing pointers to locate the desired nodes efficiently. First, we initialize three pointers: first, second, and current. As we traverse the list, we use the current pointer to locate the kth node from the start, storing it in the first pointer. Simultaneously, the second pointer is used to identify the kth node from the end by maintaining a delay of k steps between current and second. Once both nodes are identified, we simply swap their values. This approach has a time complexity of O(n), as it only requires a single traversal of the list, and a space complexity of O(1), as no additional data structures are used. This makes it significantly more efficient than the brute force method. However, it does require precise pointer management, which can introduce slight implementation complexity. An alternative to the iterative approaches is a recursive strategy. The recursive method can theoretically locate the kth node from the start and the kth node from the end by traversing the list in reverse during the recursion's unwinding phase. While elegant, this approach has its own trade-offs. In terms of complexity, it still requires O(n) time to visit each node, but it introduces an additional O(n) space overhead due to the recursion stack. This makes it unsuitable for very large linked lists, where stack overflow could become a concern. Ultimately, the optimized one-pass approach is the most efficient and practical solution. It achieves O(n) time with O(1) space, avoiding the inefficiencies of the brute force method and the drawbacks of recursion. While it may require slightly more effort to implement due to pointer management, the performance benefits make it the best choice for this problem. In this problem, we are given a singly linked list and tasked with swapping two nodes, the kth node from the beginning and the kth node from the end of the list. The positions are 1-based, meaning the first node is position 1, not 0. To solve this, we need to understand the relationship between the two nodes. The kth node from the start corresponds to the nk+1 th node from the end, where n is the total length of the list. The challenge is to locate these two nodes and swap their values or pointers without disrupting the structure of the list. As part of the solution, we also need to handle edge cases, such as when k is invalid or when the nodes are the same, meaning no swap is required. A brute force approach involves traversing the list twice, first to calculate its length, and then to locate the two nodes to swap. Let's begin by analyzing this two-pass approach in detail. After determining the length of the list, we proceed to locate the two nodes that need to be swapped. To do this, we initialize two pointers, one for the kth node from the start, which we'll call the start_node, and another for the kth node from the end, referred to as the end_node. We traverse the list again using a counter to stop at the kth position and assign the corresponding node to start_node. Similarly, we calculate the nk+1 th position and stop there to assign end_node. Once we have these two nodes, we simply swap their values. This avoids the complexity of manipulating pointers directly, which can be error-prone in a singly linked list. Finally, we return the modified list, which now reflects the swapped nodes. To improve efficiency, we can solve this problem in a single pass using a two-pointer technique. This optimized approach eliminates the need for a separate traversal to find the length of the list. We use two pointers, first _pointer to locate the kth node from the start, and second _pointer to locate the kth node from the end, but with a twist. As first _pointer moves forward through the list, second _pointer starts lagging behind by nk steps. This ensures that by the time first _pointer reaches its target, second _pointer will already be in position. Once both nodes are identified, we simply swap their values, just as in the brute force method. This approach allows us to achieve the same result in a more efficient manner while still keeping the implementation straightforward. After the swap, we return the updated list. There are several key insights that make this algorithm effective. First, the two-pointer technique is the cornerstone of the optimized solution. By carefully managing the movement of the pointers, we can identify the kth nodes from both ends in a single traversal, reducing time complexity. Second, swapping values instead of manipulating pointers is a safer and simpler strategy, especially in singly linked lists where backward traversal is not possible. This avoids issues like breaking the chain accidentally. Additionally, we must consider edge cases, such as when k is out of bounds or when the nodes to be swapped turn out to be the same, in which case no action is needed. From a data structure perspective, working with singly linked lists means all operations must be forward-only, and we rely on pointers to navigate the list efficiently. In terms of complexity, the time complexity is O(n), as we only make one traversal, and the space complexity is 1, since we do not use any additional data structures. Edge cases are crucial to address in this problem to ensure robustness. First, if k is greater than the length of the list, the kth node does not exist, and no swap should be performed. Second, when k equals 1 or n, we need to ensure that the first and last nodes are swapped correctly without disrupting the rest of the list. Third, if k equals n/2, meaning the kth node from the start is the same as the kth node from the end, no swap is needed since the nodes are identical. By accounting for these scenarios, we can guarantee that the algorithm handles all possible inputs gracefully and produces the correct output in every case. The provided solution effectively solves the LeetCode problem number 1721, swapping nodes in a linked list, by using a straightforward approach. Here's a detailed breakdown of the code. 1. Step 1. Calculate the length of the linked list. We initialize length to 0 and use a pointer current to traverse the linked list. As we iterate through the list, we increment the length variable. This step ensures we know the total number of nodes in the list, which is crucial for identifying the kth node from both ends. 2. Step 2. Find the kth node from the start and the end. To locate the kth node from the start, we initialize first_k_ node to head and move it forward, k1, steps using a loop. This ensures that first_k_ node points to the desired node. Similarly, to find the kth node from the end, we initialize second_k_ node to head and move it, length k, steps forward. This calculation works because the kth node from the end is equivalent to the length k plus 1 node from the start. 3. Step 3. Swap the values of the two nodes. Once we have references to both nodes, first_k_ node and second_k_ node, we simply swap their val attributes. This operation changes the values of the nodes without altering the structure or pointers of the linked list. 4. Return the updated linked list. Finally, we return the head of the modified linked list, which now reflects the swapped values. This solution operates in O(n) time complexity due to the two passes through the list, one for calculating the length and another for locating the nodes, and O(1) space complexity since no additional data structures are used. Edge cases, such as k being 1 or k being equal to the length of the list, are naturally handled by the algorithm. Here, we are implementing a solution to swap nodes in a linked list. We start by defining a class for the singly linked list, where each node has a value and a pointer to the next node. The main function, swapNodes, takes the head of the linked list and an integer k as input. First, we calculate the length of the linked list by iterating through it with a current pointer, incrementing a counter variable length at each step. This helps us determine the positions of the nodes to be swapped. Once the length is known, we locate the kth node from the beginning. To do this, we initialize a pointer first k node at the head and move it forward k1 times using a loop. Now, we locate the kth node from the end of the list. Starting again from the head, we use a pointer second k node and move it forward length k steps. With both target nodes identified, we proceed to swap their values. This is done by storing the value of the first node in a temporary variable temp, assigning the value of the second node to the first, and then copying the value from temp into the second node. Finally, we return the modified linked list. This approach ensures that we only swap the values of the nodes, keeping the structure of the list intact. Let's start with example 1, where the input linked list is 1, 2, 3, 4, 5, and k is 2. The first step is to determine the length of the linked list. We initialize length to 0 and set current to point to the head of the list. As we traverse through each node, we increment the length by 1. Starting with node 1, the length becomes 1. Moving to node 2, it increases to 2, then to 3 at node 3, 4 at node 4, and finally 5 at node 5. At the end of the traversal, we know the total length of the list is 5. Next, we need to locate the kth node from both the start and the end. For the second node from the start, we start at the head and move one step to reach node 2. This makes first_k_ node the node with a value of 2. To find the second node from the end, we calculate length k, which is 3, and move 3 steps from the head to reach node 4. This makes second_k_ node the node with a value of 4. Now that we have identified the two nodes to be swapped, we proceed to step 3, which is to swap their values. the value of first underscore k underscore node, which is node 2, is changed to 4, and the value of second underscore k underscore node, which is node 4, is changed to 2. After the swap, the updated linked list becomes 1, 4, 3, 2, 5. Moving to example 2, the input linked list is 7, 9, 6, 6, 7, 8, and k is 3. Again, we begin by determining the length of the list. Starting from node 7, the length becomes 1, then 2 at node 9, 3 at the first node 6, 4 at the second node 6, 5 at node 7, and finally 6 at node 8. The total length of the list is confirmed to be 6. For the second example, we now locate the kth nodes from the start and the end. The third node from the start is found by moving 2 steps from the head to reach the first node 6 at the third position. This makes first underscore k underscore node the node with a value of 6. For the third node from the end, we calculate length k, which is again 3, and move 3 steps from the head to reach the second node 6 at the fourth position. This makes second underscore k underscore node the node with a value of 6 as well. In step 3, we attempt to swap the values of first underscore k underscore node and second underscore k underscore node. However, since both nodes have the same value of 6, the swap does not result in any change. The final output remains 7, 9, 6, 6, 7, 8. Finally, let's discuss example 3, where the input linked list is 1, 2, and k is 1. We start by determining the length of the list. Starting at node 1, the length becomes 1, and at node 2, it becomes 2. The total length of the list is confirmed to be 2. Next, we find the kth nodes from the start and the end. For the first node from the start, we stay at the head, so first underscore k underscore node is node 1 with a value of 1. For the first node from the end, we calculate length k, which is 1, and move 1 step from the head to reach node 2. This makes second underscore k underscore node the node with a value of 2. In step 3, we swap the values of first underscore k underscore node and second underscore k underscore node. The value of node 1 becomes 2, and the value of node 2 becomes 1. After the swap, the updated linked list is 2, 1. To analyze the time complexity of the solution, let's break it down into its key steps. First, the algorithm begins by determining the length of the linked list. This is done using a while loop that traverses through all n nodes in the list, making this step take n time. Next, the code identifies the kth node from the start by iterating through the first k1 nodes of the list using a for loop. Since this traversal depends on the value of k, the time complexity for this step is k. Finally, to find the kth node from the end, the code calculates its position as length k and uses another for loop to traverse the necessary nodes. This step takes n k time, as it depends on the distance from the current position to the target node. Together, these steps give us the foundational time complexity components for the algorithm. Now, once the two nodes are located, the algorithm performs the swapping operation. This involves simply exchanging their values, which is a constant time operation, taking 1. To calculate the total time complexity, we sum up the contributions of each step, n, for computing the length, k, for finding the kth node from the start, and k, for finding the kth node from the end, and 1, for the swap. In the worst-case scenario, where k approaches n, the terms k and k combine to n. Therefore, the overall time complexity of the algorithm is n. Moving on to space complexity, the solution uses a constant amount of extra memory. Variables like length, current, first underscore k underscore node, and second underscore k underscore node are used, but these do not scale with the size of the input. Additionally, since the algorithm does not rely on any auxiliary data structures, such as arrays or hash maps, it operates in place on the linked list. Summarizing the space complexity, the algorithm requires only 1 space because the memory usage remains constant irrespective of the size of the linked list. This is a significant improvement compared to a naive approach, where all nodes might be stored in an array or list. In such a brute force method, the space complexity would increase to n, since storing all nodes directly scales with the size of the list. Moreover, the time complexity of the naive approach would also remain n, due to the overhead of calculating the length and performing swaps. By contrast, the proposed solution minimizes memory usage while maintaining linear time efficiency. For all input sizes and values of k, the time complexity is consistently O(n), as the algorithm always computes the length and performs the necessary traversals. The absence of nested loops or recursion further ensures that the complexity remains linear. Similarly, the space complexity is consistently O(1), as only a fixed number of variables are used. This achieves optimal efficiency for both time and space, making the algorithm robust and scalable for large linked lists. Now, let's take a look at some common mistakes developers encounter in this problem. First, many forget to handle edge cases for k. For example, if k is greater than the length of the linked list or if k is 0, you could run into null pointer errors or undefined behavior. Always ensure input constraints are properly validated. Another frequent issue is incorrect node swapping. If the kth node from the start and end overlap, meaning they point to the same node, some solutions unnecessarily swap the node with itself or introduce errors in the list structure. Additionally, it's easy to accidentally disconnect parts of the linked list by not correctly updating the previous and next pointers during the swap. This can break the list entirely. Errors in length calculation are another pitfall, especially off-by-one mistakes, which can result in identifying the wrong nodes. Lastly, some solutions unnecessarily use extra space, like storing all nodes in an array. While this approach works, it increases space complexity to O(n), which is suboptimal since the problem can and should be solved with O(1) space. Next, let's focus on interview-specific insights. A key optimization here is recognizing that the kth node from the start and the kth node from the end can both be located in a single traversal by using two pointers. This eliminates the need for multiple passes or auxiliary storage, making the solution efficient. Interviewers may also ask follow-up questions, such as how you would handle the scenario where the linked list has an odd number of nodes and k corresponds to the middle node. It's important to clearly explain your logic for such edge cases. Often, the discussion will center around achieving O(n) time complexity in O(1) space. Being able to articulate why your approach satisfies these constraints is crucial. Additionally, problems that involve identifying nodes at specific positions, like kth from the start or kth from the end, often rely on two-pointer techniques or leveraging the total length of the list. Recognizing these patterns can help you solve related problems more effectively. Speaking of which, you might want to explore related problems like removing the nth node from the end, finding the middle node of a linked list, or reordering a list, as they build on similar concepts. Finally, let's explore some alternative approaches and their trade-offs. One common method is the two-pass approach, where you first calculate the length of the linked list to identify the kth nodes, and then traverse the list again to locate and swap them. This approach is straightforward and easy to implement but requires two full traversals, resulting in O(n) time complexity. On the other hand, the single-pass approach using two pointers is more efficient. By advancing one pointer ahead by k steps and then moving both pointers together, you can locate the kth node from the end during a single traversal. This achieves O(n) time in O(1) space, making it optimal, though slightly more complex to implement. Lastly, there's the array-based approach. Here, you store all nodes in an array, which allows for direct access to the kth elements for swapping. While this simplifies the logic for identifying and swapping nodes, it requires O(n) extra space and is less suitable for larger lists. Each approach has its own pros and cons, so it's important to choose the one that best fits the problem's constraints and the context in which you're solving it. Great work! To summarize, we've tackled a linked list problem that emphasizes traversal and node manipulation. This problem reinforced key concepts like efficient traversal and edge case handling. Thanks for joining, and don't forget to like and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!